Hi everyone. So we are back from vacation, back to reality, and we are now going to learn how to solve systems of equations by substitution. So here we go. If you are in my class, we had a warm-up. We watched a video on Edpuzzle, video number 1, giving us a little introduction to systems of equations by substitution. Now we're going to take some notes on these on substitution. Then you'll have another video to reinforce it and an in-class assignment in their breakout rooms. So here is our warm-up, and you can do this on Go Formative. Take a break or go ahead and pause the video and then come back if you're in my class. Otherwise, you can just follow along with me. So we were doing a couple of little practice problems. If a equals 10, then what is 3 plus a? So we substitute in the 10 for the a, and we have 3 plus 10, which equals 13. On b, what is 2 times a? If a is 10, we substitute in the 10 for the a, and we have negative 20. And then the last one on this is what is 5a plus 4? If a is 10, we substitute in 10 for the a, and we have 50. 10 times 5 plus 4, which gives us 54. So these are the answers to those 3 problems. The second question, the third is related to the second, but I had to separate it on Go Formative, is to graph these 2 equations, remembering, since we've been on break, y equals mx plus b. M is your slope, b is your y-intercept, where we begin. So on this first one, our m is equal to 2, and our b is equal to 3. On the second one, our m is equal to negative 1/2, and our b is equal to negative 2. So let's go ahead and graph these. We begin at 3, and when we have a slope of a whole number, it goes over 1. So our slope is 2 over 1. We rise 2 and run 1, rise 2, run 1. And I continue to do it in the other direction in the same pattern. So I can graph a nice line. And now the second one is we begin at negative 2, and we have a negative slope of 1/2. So we're rise over run. We're actually going to drop 1 and rise and run 2, drop 1 and run 2 in this direction. And we do it in the other direction in the same pattern. Rise 1, but run 2 to the left. And we graph those points. And for some reason, it is not showing. All right, well, my internet stopped right at that point. So hopefully now it's caught up, and we can see our solution is right here at negative 2, negative 1. You can zero in on where we are crossing. All right. So we are going to just reinforce the same thing I've been reinforcing all semester, which is our m in our y equals mx plus b is our slope, and our b is our y-intercept. We have 3 types of solutions to systems of equations that we've talked about for a few different classes. We have one solution where our lines intersect. We have no solutions that are parallel lines. And we have infinite solutions where the lines are on top of each other, the same line. So intersecting, parallel, and the same line. All right. What is the substitution method? So let's think about it. Have you ever had a substitute teacher? When the regular teacher is gone, you get a substitute or replacement teacher in their place. It's the same basic idea here with systems. One thing is taken out and a substitute or replacement is put in its place. Today we will look at 3 different examples of this method. So far, we've learned one type of systems of equation method to solving them. There are 3. There's the graphing, where we would graph 2 different lines and look at where their intersection is, if there is an intersection. And now today we are going to do the substitution method, where we are going to isolate a variable and solve by plugging it in or substituting. Now, in this class, you will only be given equations that have an isolated variable. You will not have to solve and find an isolation, but you will next year in your classes. And then the next part of this is the elimination, which we will do in the next couple of classes. There are 3 steps. There are 3 steps to solving linear systems of equations by substitution. There's actually 4, but the first step we are not going to do in this class, and that step would be solving, this would be, let's call this 1A, solving an equation, oops, for one variable. And that would be something like y equals, a equals, x equals, p equals. So they would already be solved for one equation. And we would always want to choose the easiest one, but that will be done for us. So our steps are to substitute, replace, plug in, solve the equation, step 2, and plug back in to find the other variable. Oh, I ran out of room. And for your last step, we could call this 3B, is to check. We always check, so that's why I didn't write that down as a specific step. Alrighty, so the substitution method is merging 2 equations together by substituting. So at least one of the equations needs to have an isolated variable, which I'll go over in just a second. But the idea is that if y equals 5, just like in our warm-up, and we want to substitute in the y, which is this y, we want to substitute in that 5. So we could merge these equations together to have it look like this. And then we could solve, which we're not going to do on this actual page here. Over here on the second one, I know that y equals 2x plus 1. And here I have this y and this y. So I can substitute in 2x plus 1 into that y. It's not just one number, but I can still substitute it in. So I would have, merging these together, x plus 4 times 2x plus 1 equals 6. As you can see, I have substituted in, replaced the y with what I'm told the y is equal to, 2x plus 1. So we have to have our variables isolated. And so what I wanted to do in this slide is to determine what is a variable isolated look like. So when I'm talking about that, I want to have as I set up in the previous screen up here, it looks like this, a y equals, oh, I'm lagging, a y equals, an a equals, an x equals, any letter equals. So it's having the letter the variable alone on one side of the equal sign. So when we look at number 1, these are x and y. They are alone. They have a 1, an invisible 1 in front of them, but they are together on one side. So this is no. It is not isolated. Number 2, we have y alone on this side, so this is isolated. Number 3 kind of looks like number 2 because I have that same y, but on this side it's being added with the 2x, so this is no. Number 4, it's just y equals 7. It can equal just one thing. It's isolated. So we write yes. Number 5 kind of looks like number 4. Y is alone on the side, but it has a 2 here. So this is no. Number 6, there's only one x, but it is being combined with a -6, so this is no. Number 7 looks like number 6 because of this y minus 4, but it does have the x isolated on that side. So this one is yes, it is isolated for the x. And that is the same as number 8. You have a y with the 24, so that part is no, but this part, it is isolated. So yes, the whole thing is isolated for x. All right, let's get into some examples. We have 3 different examples. This particular example has both of the equations isolated. The first one for y, the second one for x. So I could plug in only one thing, and that is, since I only know what the x is here, I have to plug it in over there to that x. I can't plug the y into anything into the second equation because there is no y. So therefore, to put these together, I'm going to say that y equals -2, and I substitute in that 1 for my x, since 1 equals x equals 1, and I solve, and I get y equals -2 plus 5, or y equals 3. So this, if I were to graph it, and this is actually a pretty easy one to graph, I have one equation, the x equals 1, is just a vertical line at 1. So therefore, my other line, let's do it in green, I would begin, and this is just a very quick graph, and it's -2, 1, -2, 1, -2, 1, about there. And so I would be having a line going right here, and the place that I am going to have a solution where I'm going to intersect is at 1, 3. Well, my x is 1 and my y is 3. My solution is 1, 3. I already knew what x was. It told me up there. So let's try a harder example. Example number 2. Example number 2. I see that in this first equation that I have an isolated variable. That means that y equals x minus 4. So I can take this x minus 4, which is equal to y, and plug it into my y, substitute it. So I end up with x plus x minus 4 equals 10. I don't need parentheses there because we're not multiplying or dividing anything. I just put them there so that you could see that that is what I substituted in. So now I have to combine like terms, use distributive property, and simplify and solve for x. No distributive property, just an x plus x, which is 2x, minus 4 equals 10. If you want to put your line down, that's fine. You add 4 on both sides. What you do on one side of an equation, you always do on the other. You're left with 2x equals 14. Inverse of multiplication, oh, I jumped up in my head. Divide by 2 on both sides. 2x over x is 1x, so I just write the x is equal to 7. Now I know what my x is, So in my solution, my x comma y, I know that x is 7. But now I have to figure out what is y. So if I look back into my steps that I wrote way up here, I substituted, I solved the equation, and now I need to plug back in to find the other variable. So let's scooch back down here. So now that I know that x is 7, I have to find y. I can plug it into either one of these equations, but since I know that this first equation is saying y equals, and I know what x is, that's just the easiest one to plug it into. Always look for the easiest. So y equals x, which I am now substituting in my 7 since I know that x equals 7 down here, and then minus 4. So y is going to equal 3. And I can take that and replace my solution with that, 7, 3. Now you can do a quick check. We just solved this first one, so we know 7 minus 4 equals 3, and I can plug them back into the second one to see if it works. Does 7 plus 3 equal 10? Yes, it does, so it checks. Let's try our last example. And I put parentheses around the x. I don't know why. It was maybe just to make you see that there could be parentheses there. It doesn't change anything. The second equation has the x isolated. So therefore, I am going to substitute in 5 minus y for that x. So this first one will now be 5 minus y minus 2y equals 8. And doing that, I have to solve for y, combining like terms. So I get 5 minus 3y equals 8. I can put my line down the middle if that helps. Subtract 5 on both sides. And I have 5 minus 5 is 0, so negative 3y equals 3. Inverse of multiplication, divide by negative 3. Negative 3y over negative 3 is 1y, but I don't have to write the 1. And on the right is negative 1. So once again, my solution is an xy, and I just found out what was my y. So I can go ahead and put in negative 1 for my y. But now I need my x. So now I am going to take that negative 1 and I am going to substitute it back into that second equation because I'm looking for x. I could do it into either one, but it would take more steps. So since I want to know what x is, and this says x equals, I just plug it in. 5 minus, and my y is a negative 1. So I end up with 5 plus 1, or 6. X equals 6. So now I can put 6 in my solution. And let's check it out. We did just check it on the second one, but let's check it on the first. So this is a check on the first one, which was x minus 2y equals 8. Whoa, that was interesting. There we go. All right, minus 2y equals 8. So we are going to substitute back in, and we have 6 minus 2 times negative 1. What does that equal? Well, that is going to be equal to 6 minus 2 times negative 1 is plus 2, and that equals 8, and it checks. So there you go. There are 3 examples, and on the video as well as on the practice example or practice problems, they're going to get a little bit harder, and we will go over them more the next class. I hope to see you next time. Bye-bye.